It's a pleasure to be back in India after 20 years and realizing that we should have done this much sooner. I'd like to talk to you about the history behind some work that I did with Patty quite some time ago, and how it has influenced many things that I have done both before I first came to India to work with Patty and afterward. So I'm going to talk to you about piecewise conserved quantities and applications to two broadly different areas of relativity. So the history is that in 1987, both my wife, Corinne Minogue, who's here, and I were Indo-American fellows and spent several months in what we were then told to call Madras, in Chennai at the Institute of Mathematical Sciences, and then later with the Theoretical Astrophysics group at TIFR, which is where we met Patty and began working together, and had the pleasure of coming back and spending some time in Pune and at the Raman Institute in Bangalore. And as you see here, Patty and I did work together on conserved quantities from piecewise killing vectors, so piecewise conserved quantities, which is the theme of this talk. So that paper was submitted in 1988, so not quite 30 years ago, but pretty close. Continuing the history, prior to coming to India, I had been a postdoc with at Hooft in the Netherlands, and I'll tell you a little bit about the results that we had come up with at that time that involved joining spacetimes together in an interesting way. As you'll see as I go into a little further detail as we go along, the key issue there is that we're joining things along a null surface, which was a little different from the more traditional joins along space-like surfaces. And so a couple of years later, when we were in England, Chris Clark and I kind of polished up the mathematics of how to do null junction conditions. And then that all set the stage for this work with Patty. Followed a year or two later by a paper with Pankaj Joshi generalizing some of these results to other kinds of black holes. I hope you have been paying careful attention to these slides. I was young in those days, and there were a couple of things I didn't know. One of them was how to spell Nordstrom, okay? And the other was how to hyphenate names and the difference between hyphenated single names and hyphenated double names. So if you look carefully, the length of the hyphen has changed between those two signs. All right. So older, wiser, smarter, better with technology, all of those things. But this story continues in another paper very much in this series, which was 20 years later, 2010, a master student, Jeff Hasboon, and I went back to those early results with at Hooft and considered cases with negative energy. And you'll see, as I'll show you in a moment, that there are some differences in the results that are quite striking. So you should now ask, what was I doing in the intervening 20 years? For part of that time, Corinne and I and others were working on signature change, where you join regions of space-time of different metric signatures, so Euclidean regions to Lorentzian regions. And I'll tell you a little bit about what the physics represented by such a scenario might mean. Corinne and I worked largely with Robin Tucker in England, and independently, George Ellis and his group in Cape Town were using these ideas for cosmological models, and the two groups later got together and, oops, I'm sorry, wrong button. And so we later have written papers combined with George Ellis, Charles Hellaby, and a few other people, but there's a series of papers in the 90s addressing issues of signature change and what the implications might be. All right, so here we go. Here are these two scenarios. On top are the results with at Hooft, showing how to combine Schwarzschild regions along shells of matter. And they are, you saw these in an earlier talk. If you take two Schwarzschild regions and you drop in a shell of matter, null matter, whatever that might be, this is a an idealized model of some matter falling into a black hole. And of course, what you expect to happen is that you will increase the mass of the black hole. And so the mass on this side is less than the mass on that side. You can do the opposite as well and think about matter coming out of the white hole, if you will, decreasing the overall mass of the Schwarzschild region. And the most interesting case, you can drop in matter along the horizon where the mass does not change. Let me emphasize that the very first model we had in this category, and I should say that this was a Hooft's model where I got to contribute by working out some of the mathematical details, but it was entirely his idea, was that in this particular case, you don't have to use a spherically symmetric shell to drop in. You can drop in a single massless particle at the north pole of the sphere, say, with a shock wave that is along the rest of the horizon, and you still get the same result of increasing, or not increasing, of being able to join two equal mass Schwarzschild regions along this shock wave, if you will, being created by a single infalling massless object. I emphasize this example because, to the best of my knowledge, this is the closest thing there is in GR to an exact two-body solution. And it's a two-body solution in the sense that I'm thinking of the background Schwarzschild region as one particle, and a test particle falling in. It's a null particle moving along a null geodesic, and the full back reaction is incorporated into this model in the sense of the shock wave at the horizon. And so it's, you know the story about progress in physics, that in Newtonian theory, you can solve the two-body problem, and in relativity, you can only solve the one-body problem. Well, this is as close as there is to a two-body solution in GR. You of course know the punchline to that story, which is that in string theory, you can't solve the one-body problem. Anyway. The signature change example, this is more a picture from the Ellis cosmological approach. The idea is you're thinking of this is an attempt to portray the early universe. It's hard to see in this picture, but there is a line marked on this paraboloidal object where your surface changes from being less than at 45 degrees to greater than 45 degrees. There is an entirely Euclidean cap on an otherwise Lorentzian spacetime, and the idea is to model something other than the Big Bang by having the universe start off as an entirely Euclidean object that makes some sort of transition to a Lorentzian spacetime at some springing into existence at some finite radius. And again, the idea is the question is, what does it mean to join a Euclidean signature metric to a Lorentzian signature metric? So all of these things are about joining regions of spacetime together. Okay, a little more detail. I'm not going to go into very much detail here. As has been pointed out in a couple of talks today, there is a well-known formalism for joining spacetimes. This goes back to Israel and Lichnerowicz and others, where you have two spacetime regions. I'm assuming for the moment there's a space-like surface that divides them. You have smooth metrics on either side. You have some notion of a discontinuity where those two metrics join, but you assume that the metrics match continuously at the join, and that allows you to construct a distributional curvature tensor, and so you get the usual Ricci tensors on both sides, and then a surface distributional stress energy, or in this case curvature representing the stress energy that would be associated with whatever matter might be on that shell that divides the two regions. Okay? What was interesting in the work with Hooft is we had to extend these ideas to boundaries across null surfaces, and as many of you know, and as was pointed out among other things in the talk just now about boundary terms to the Einstein-Hilbert action and its generalizations, Funny things happen on null surfaces. You have to start paying careful attention to what you mean by normal vector and what you mean by tangent vectors and when those are the same, et cetera, et cetera. But the same basic idea holds. And here is a more careful picture of that solution that Ed Hooft and I worked on, where you have a shell of matter along the horizon joining two Schwarzschild regions. And one of the things we had to check very carefully was how do the horizons, the other horizon, if you will, line up? And the answer is they don't. There's a mismatch. And one of the things we wondered was, would that allow you to traverse from one universe into the other? And the answer is no. You get to traverse from the white hole region into the black hole region, which doesn't help you very much. But so there is a narrow band here where, avoiding the horizons, you can nonetheless change regions in ways that you weren't expecting. And the recent work with Hasboon shows that, unlike in the Ed Hooft situation, if you allow for a negative energy shell, of course, the shift goes the other way, and suddenly you actually have a way to pass from one universe to the other. So this is yet another in a series of models where, if you did have something like negative energy density, you can construct some sort of traversable wormhole. So what does this have to do with the work with Paddy? Well, Paddy and I considered what would happen if you try to examine symmetries in the sense of killing vectors, but now it's a piecewise killing vector. You have a killing vector in your two regions, but you now have a notion of what happens at the join, and you have a discontinuity in the killing vector. Then you might get singular terms that are going to be interesting statements about symmetries or lack thereof. If you imposed Armois junction conditions, so you're now assuming not just that the metric is continuous, but that the extrinsic curvature is continuous, then the stress tensor, the surface term, is zero, and you nonetheless have a surface term showing up in your conservation law. And that surface term is coming from the discontinuity in the killing vector. And so to recover a conserved quantity, there are several assumptions you can make. The assumptions that we made is assume that the discontinuity in the killing vector is normal, i.e. tangential to the surface, the null surface, and that also the double null component of the stress tensor in that direction is zero. And with those assumptions, you would recover a truly conserved quantity from a merely piecewise symmetry. Okay. Several years later, Charles Helleby from George Ellis's group and I were trying to put together all the pieces of what had happened with signature change, and we realized that there's, of course, a divergence theorem that holds in this case, and you just have to go back into the guts of how you prove the divergence theorem to begin with, and the cleanest derivation turns out to be using differential geometric language involving differential forms, but don't let the language here throw you. This is the standard divergence theorem telling you that if you integrate the divergence over some region, you're going to get a flux term over the boundary where you have to think a little bit about do you have inward or outward pointing normal vectors, and what are the induced metrics and things like that if you have two regions that you're joining through one of these discontinuities. But if you have a piecewise smooth vector field, you recover the divergence theorem in this form. We call this the patchwork divergence theorem. And there is a new surface term on the boundary, not just around the outside of your box, which corresponds to the discontinuity in the vector field that you started with. So nothing surprising there. Working out the details is a little bit tricky. So moving on, there are two applications you can make of the patchwork divergence theorem, and one of them is to go back and say, well, we have a piecewise killing vector. So here are two Schwarzschild regions joined across a null boundary. Here are the two Schwarzschild line elements written out. There's an assumption that the metrics should match along the null surface. That gives you a condition. You now take the two killing vectors on each side. This is just d by dt expressed in double null coordinates. The discontinuity satisfies the condition we made about which way it points. You work out the stress tensor, the double null components satisfy the condition that we had. Everything works out just fine. You recover a piecewise conserved quantity in the spirit of Patty and my work. And of course, the conserved quantity tells you that the energy density, the mass, if you will, of the infalling shell is precisely the difference in masses between the Schwarzschild regions. Again, no surprises, but a little bit nice to put everything together. Signature change can be handled the same way. The interesting thing about signature change is that the volume element that shows up in a key piece of the divergence theorem is continuous. The volume element is the 4D, so the 3D volume element of your space-like surface times dt, and the dt in the volume element doesn't care about the sign of your line element. So that's remarkable, that even though you have this very horribly discontinuous line element, you still have a continuous volume element. But if you go ahead and you work out the Darmois junction conditions, what goes wrong is a factor of plus or minus 1, not continuity of the curvature, not continuity of the extrinsic curvature. What goes wrong is the signature is not continuous. And so you wind up with a discontinuity, a surface energy density, if you will, at the boundary due to the signature change. And okay, don't ask me what energy density in a Euclidean region means, but there's nonetheless a notion of energy density showing up at the surface, even though you've satisfied the Darmois boundary conditions where you would normally expect to have no surface term. And again, the patchwork divergence theorem here would fit the bill. I'm sorry, say that again.
The signature change of the metric, will it also imply the energy density going from positive to negative?
No, it's that the sign of this contribution to the energy density, the Ricci scalar of the surface, the sign of that contribution changes. So depending on what your extrinsic curvature is, yes, that could change the sign, but I'm assuming that this term dominates. And so this is a small contribution, but it is nonetheless a non-zero contribution. But I don't think I can make a statement about the changing sign of the energy density. Let me follow you up on that with you later. Okay. Let me now switch gears for a little bit. There was another 10-year gap in my personal history there. And during part of that time, both Corinne and I set off on a slightly different path, which is to study how students learn mathematics and physics. And I would like to relate some of that work to what I've just told you about, and in particular emphasize the importance of geometric reasoning. And the first thing that I would like to comment on here is the following. Iedereen in deze kamer kan twee talen praten. Let me tell you what I just said. Wrong button. What I said is that everyone in this room is bilingual, except I said it in Dutch. Okay? And what I mean by that is not that you all speak English and Hindi and probably Marathi and Tamil and I don't know how many other languages, but rather that you're all physicists. And you therefore speak both physics and mathematics. And you're bilingual probably without knowing it. And one of the questions that we set out to ask is, how do students make that transition from speaking mathematics to speaking physics? And in a nutshell, what we learned is that mathematicians tend to teach algebra and physicists tend to do geometry. And as a geometer, of course, this makes me very happy. But I just want to comment very briefly that we have done quite a bit of work in trying to understand and convey to teachers of mathematics and physics what some of the issues are in making this transition. And I'll refer you to two websites one for vector calculus, one for the entire physics major as it is taught in an American university, where you can find more information about some of the things that we've done. Question?
You think the mathematics the language, but the physics the science?
I think I'm going to pass. What I'd like to tell you here is a very small piece of how some of these ideas relate to what I just said. I'd like to talk about an elementary example, elementary for the folks in this room, which is Lorentzian vector calculus, and ask you to think about trying to model ordinary Euclidean geometry, except it's not Euclidean, it's Minkowski, and it's Lorentzian. I've changed the signature. And as we all know, here I have the standard orthonormal basis of vectors, except one of them squares to -1. We know how to deal with that. But vectors and even the divergence, there are no funny signs anywhere in those quantities. And I can go ahead and I can write down the ordinary divergence theorem in this three-dimensional universe, 2 + 1. And as you all know, when you teach or learn the divergence theorem, you take the outward flux. And of course, you may not have thought about it, but that's only true in space-like directions and not in time-like directions. That in fact it's the inward normal on time-like, for space-like surfaces when the normal vector is time-like. And we rarely ever think about that because the only time you consider such sandwiches, you're ignoring the pieces at infinity, you're only caring about two space-like surfaces, and it doesn't make any difference whether you take two outward or two inward pointing normal vectors. And my point here is that this is an elementary toy problem where you can think about understanding this piece of mathematics that has huge implications for physics in terms of tweaking the context just enough to force you to think about it outside of your comfort zone. And that's exactly the kind of strategy that we use in the classroom. So let me summarize what I've told you. Junction conditions on null surfaces are not quite what you expected. There are some surprises, including what negative energy shells can do to black holes. Signature change is even more surprising. Even having continuous extrinsic curvature, you don't necessarily get the absence of a surface layer. Minkowski space is surprising. The divergence theorem in Minkowski space is not quite what you expected unless you've thought about it. So there's three conclusions all coming out of this work. And the most important one is that the patchwork divergence theorem, which Charles Helleby and I came up with, and incorporates the work that Patty and I did, and in fact incorporates all of this work on both shells and signature change. So there's the scientific summary. Working with Patty was a whole lot of fun. There's the personal summary. And I will stop there, pointing out that both this talk and the paper on which it's based are available online. Thank you.
And I was interested in your statement about when you, I guess then, you talked about a negative energy shell, and then you're able to transverse a black hole. Does that mean if I have a black hole embedded in a lambda less than 0 universe that I can do this? Is that what you meant by negative energy shells, or? So
here we're doing classical GR, where it's, I'm talking about a mythical, so first of all, even on the left, I'm talking about some mythical notion of massless matter that moves at the speed of light, right? So I don't know what that is.
Photons?
Maybe.
Okay. All right.
Okay. And in this model, I'm now assuming that that same shell has negative energy. And if you tell me photons again.
Same shell. When you say the word shell, you.
It's a spherical shell of matter of radius 2m. It's sitting at the horizon.
I see.
It's not collapsing. It's not collapsing in these two cases. It is so in these pictures on the left and right, these are both. This is a collapsing and this is an expanding shell, but the example in the middle is sitting at the horizon at constant radius They're all moving at the speed of light. This is a toy model for what would happen if you dropped in more physical matter. Can I do something like this in the context you suggested? I don't know, but I would expect that this truly requires localized negative energy.
Or global negative energy?
No, I suspect it requires low, but I don't know. The very good question is whether I can do some, violating some average energy condition would be enough. Whether it has to be uniform negative energy, I don't know.
No. From your that signature change. No, I was wondering that from this signature change exercise, what is the ultimate statement? Did you learn anything?
So there are two situations that were studied. I alluded to the one that motivated Ellis's group working in cosmology, which was to attempt to model a creation of the universe without invoking a Big Bang. And they, it's not at the status of this is a working mechanism, but they were able to argue that if this happened, then you could put some constraints on how what the model would look like. So this would be for a Robertson-Walker model that starts at a finite radius, and then the conversion to from Euclidean to Lorentzian signature involved some sort of exponential damping of the Euclidean side of things. What motivated Corinne and I and Robin Tucker was trying to understand how scalar fields would behave with such boundary conditions. And what we discovered were some interesting facts about Bogolyubov coefficients. If you would start with the Lorentzian region, propagate through a thin Euclidean sandwich and wind up in another Lorentzian region, you could make statements about particle production in the sense of Unruh detectors in such a space-time that turns out to depend only on the width of the Euclidean region. But these were, in both cases, these are toy models that would only be relevant if one could come up with a mechanism as to why those Euclidean regions should exist to begin with.
There are no more questions. That's fine. Thank you.